Okay, so I can start? Okay. So yeah, in this talk I will present an improvement of the efficiency of acoustic simulation of the vocal tract shape. So a little bit of context. So as you know, the speech process can be seen as a source filter process in which the vocal tract plays the role of the filter by enhancing some part of the source spectrum with its resonances. And we can predict this filter part with acoustic simulations and compute the transfer function which constitutes the filter. So the most used approach for this is to do a one-dimensional simplification of the problem. So we consider that only plane wave propagates in the vocal tract, and under this assumption we can simplify the vocal tract shape by considering only the cross-sectional area of the vocal tract. So this is a so-called transmission line approach. It is very efficient, it runs in real time, and it's very widely used for speech research. But it has some limitations. So the first one is, since we simplify the vocal tract shape, we cannot simulate precisely the vocal tract geometry. And the second one is, since it relies on the plane wave assumption, it cannot simulate properly the 3D acoustic field at high frequency, and it is valid only up to about 4 or 5 kHz. So if you want to overcome these limitations, you need to use a 3D approach to do acoustic simulations. And the most popular one for this is probably the finite element method. But this method has some drawbacks also. And the main drawback is computational resources it requires. So to illustrate that, if you want to solve the acoustic problem in the frequency domain, you will need about 10 hours to compute 1000 frequencies with one processor on a standard laptop. And we can also speak about memory requirements. So this kind of problem involves a lot of degree of freedom. And if you want to obtain a given accuracy with your own laptop, you may be limited because your memory doesn't allow to solve the problem with as many degree of freedom as you would like. So the aim of this work was to develop a simulation method which has the same degree of accuracy as finite element, but that you can run on your personal computer without waiting days for the result. So how did we do that? We relied on the multimodal method. So in this context, multimodal doesn't refer to a combination of auditory and visual cues, but it's a specific physics simulation method. So the fact is that very fast 3D simulations already exist for acoustic problems, but for very simple shapes. So let's see in a bit more in the details how this works. So this works on the projection of the acoustic field on a basis of eigenfunctions. So this is somewhat similar to decomposition on Fourier series, as illustrated here. But in this case, you don't have Fourier, you don't have sine and cosine functions, but more specific function in 2 dimensions, which describe the acoustic field on the transverse plane of the tube. So you have examples. I don't know if this works. Examples here, and on the very left here you can see the so-called plane mode, which is a uniform function over the cross section, and then you can see other more complex functions with increasing complexity towards the right. Another thing to know is that to each of these functions, which are called transverse modes in acoustics, is associated cut-on frequency, which is 0 for the plane mode and which increases with the complexity of the shape. So the acoustic field can be expressed as an infinite summation of these transverse modes, weighted by their amplitude on the local place on the propagation axis. And if you want to solve the acoustic problem using this description, first you have to truncate this infinite summation and consider only n propagation modes. And this yields a set of n coupled differential equations in which the acoustic pressure is related to another physical quantity, such as particle velocity or the acoustic potential. And this is this set of differential equation is related by a matrix that I name M here, which is built from the wave equation and the boundary condition of the problem. So, as I mentioned before, this works for simple shapes such as cylinders. And now the question is, how can we simulate a complex shape? So the solution we use is to slice the vocal tract shape in segments, as illustrated here. In each segment, we consider that the contour is constant, and we compute the transverse modes using two-dimensional finite elements. So at this point, you may think that we use again finite elements and it will decrease a lot efficiency, but in fact, it's not the case, because here it's a two-dimensional problem, and the number of degrees of freedom is much less than in 3 dimensions. And as a matter of fact, computing the transverse modes for about 100 segments will take about a few minutes only for using a regular laptop with one processor. And once we have the transverse modes, now another problem is how to take into account the curvature of the segments and the variation of cross-sectional area. And this we do using a geometrical transformation, which will make the segment become straight, and which will compensate the variation of cross-sectional area. This geometrical transformation can be characterized by its Jacobian matrix, and this Jacobian matrix is used to transform the wave equation to express it in the transform coordinates to obtain the equation on the bottom. And this transform wave equation is used to build the matrix M in this set of coupled differential equations and to solve the problem. The last step is to connect the segments, and this is done by using the condition of continuity of the acoustic field as interface between the segments. So, of course, we have watched the convergence of this method. So, for the vocal tract shape, the relevant parameter for the convergence is not directly the number of modes which is used, but rather the maximal cutoff frequency that we consider. So we consider all the modes up to a given cutoff frequency. And this is so because you don't need the same number of modes to solve accurately the problem for small segments and for big segments. And in this figure, you can see 3 curves which correspond to different limit cutoff frequencies. The first one is with 0 and obviously corresponds to only the plane mode, which is kind of equivalent to the transmission line method. And the 2 others correspond to a limit of 20 kilowatts and 40 kilowatts. As you can see, it's not sufficient to put the upper limit of cutoff frequency to the maximal frequency that you want to simulate. You need more propagation modes. And regarding the efficiency of the method, with our implementation in its current state, we achieve about 1 hour for 1,000 frequencies. So it's about a factor of 10 compared to finite elements. And obviously, after that, we compared the outcome of this method with finite elements and the transmission line method. We have computed the transfer function of different vowel geometries, and the fact is that the agreement between the three methods depends on the vocal tract shape. So you have an example here with the schwa, in which the agreement is relatively good for all the three methods. So in black, the finite elements, in red, the multimodal, and in blue, the transmission line. Also, please don't consider the losses for the transmission line because it was not exactly the same model. So it is the higher peak at low frequency or not intrinsic difference. If we consider the vowel U, we have the opposite example in which we have the worst agreement. And but we can see that the three first resonances are relatively similar between the three methods, which confirms that the transmission line method is relatively good at a low frequency. At higher frequencies, there is a better agreement between the proposed method and the finite element, but still significant differences. And if we look at the vowel E, we have an average case, I would say, in which there is less difference, and in particular less difference between finite element and the proposed method, but still in some frequencies some significant difference. So why are there still differences between the proposed method and the finite element? So obviously there can be several reasons for that, and the first one can be that the slicing process, even though it ends in a geometry which is very similar to the one simulated with finite element, is still a little bit different, so it can induce some differences. And the reason could be some phenomena which are not still not properly simulated, such as junction between the segments, or it could also be some intrinsic limitation of the proposed methods. So in conclusion, we have successfully developed a method which is more efficient computationally than the state-of-the-art methods, but there remain some significant differences that need to be better understood. And we also need to validate these simulations by comparing it with acoustic measurements on real replicas. And in the end, we would like to apply this method to perform articulatory synthesis. So thank you for your attention. And now if you have questions, I will be happy to answer them.
Okay, are there any questions in the room? Please.
Hello, thank you for your talk. What's the relevance of making it work on a CPU in the era of GPUs, where you see GPUs everywhere and you can parallelize whatever algorithm you have? What's the...
Well, I think the relevance is to make this kind of simulation more accessible. So I think for most of the people here, it's easy to use machine with several cores to program on GPU. But for people who don't know a lot about informatics, you need just a program in which you will click on some buttons and get some result. So I think that's the main relevance. And then it's not an intrinsic limitation to apply this method on one CPU. You can also apply it on multi-core architecture. It will be even more efficient, of course.
Thank you.
I think we have a question online.
Oh, yes.
So there's a thank you for this very interesting talk from me and from the question here. How about boundaries how are boundaries implemented in the multimodal simulations?
It's the same boundary type as in the finite element, so it's impedance boundary condition.
There's another one. Finite element method should also have some computational errors. Did you check at the accuracy of finite elements method?
Yes, of course. We ran some convergent tests and we ensure that the solution was converged.
So there are no more online questions so far. Any questions from the audience? Okay.
Thank you. Discrepancies are for closed vowels. So is it a coincidence, or maybe the presence of a construction may cause these discrepancies?
Yes, probably it's related to that. It's not very clear how, however, so far.
I don't see why it could be a problem. For some time I suspected a junction between the segments, so there may be something in there, but because the junction have a star-like shape, because of the slicing process, and in the finite element it's smoother, so it could introduce some kind of difference, but the reason is not very clear so far. Okay, and have you tried on consonants, such as fricatives or?
Yeah, I've tried, yes. So it's just another type of transfer function, I would say. It doesn't have such a big difference with vowels.
Do we observe such differences between methods?
We haven't tried the comparison with finite elements. Sorry, I didn't understand.
Okay, thank you.
So I think we still have time for one. Do you have another question online? No. A couple of questions. Are there any further questions? Doesn't seem to be so. Then let's thank the speaker again.